Hello everyone. So, we will continue our discussion on X-ray diffraction. So, what we have learned so far? First of all, starting from how X-rays are generated, right, and how we make use of X-rays to understand the material, right. Basically, we discussed how do we get characteristic spectrum, right. Then we talked about crystallography, basics. We did not go in detail, but basics of crystallography like lattice, we looked at unit cell, different crystal systems, space groups, right. Then we talked about diffraction. What is diffraction? We talked about Bragg's condition which gives you diffraction, right. So, you can think of it as constructive interference, right. There is a condition which has to be met. If it is satisfied, you get diffraction. So, now we know that you get diffraction from a crystal, right, and that dependence, like dependence of the plane and the incident angle is dictated by that relationship we talked about. When you combine two relationship, one is Bragg's condition, lambda equals to 2d sin theta, and another one is interplanar spacing, right. So, when you combine these conditions, you can get relationship between incident angle and the diffracting planes, right. So, we know now, okay, if you have an X-ray, you will get diffraction from crystal, could be polycrystalline material also, where you have different crystals together. In the last lecture, we discussed about what gives rise to the difference in intensity. So, we talked about you are getting diffraction, right. So, you know that I am just simplifying this, right. It is, suppose you plot intensity 2 theta, we know where we are getting these angular values from, right. It is coming from your diffracting planes. Now, we talked about what gives rise to this difference. In this case, your intensity is dropped, further dropped here, increased. So, there is a difference in the intensity. So, to understand that, we talked about various factors which we have to take into account. For an example, polarization factor, structure factor. We looked into structure factor where you calculated the structure factor F, right, for different unit cells, right. So, we talked about Lorentz. Usually Lorentz is combined with the polarization, you call Lorentz polarization factor, right. Multiplicity factor, it depends on the planes. Some planes are more likely to diffract than others, right. So, there is a factor, multiplicity factor, which you have to take into account. Absorption, part of your X-rays will be absorbed by the sample. So, it is important to know this absorption phenomenon, right. Similarly, temperature, because the temperature will affect your thermal vibrations. So, that also will contribute to will affect the intensity. So, in general, if you have to write this intensity in simplistic terms, right, you already know structure factor you have calculated, right. So, it is proportional to structure factor square, right. You remember when we did classroom exercises, few exercises, you calculated the structure factor, right. Then we said structure factor to the power 2, right. So, and then you have a multiplicity factor M, right, for given HKL. We are talking about a given HKL plane, right. Then you have Lorentz polarization factor. You combine basically Lorentz and polarization factor. You have absorption factor and you have a temperature factor. So, this is a simple relation which connects intensity to various factors, right. If you know all these factors, you can calculate intensity, that is the idea. In some cases, you will have one factor dominating others, but these are important factors you need to consider, okay. We will keep coming back to this equation because that is a very important relation. That is what tells you what will be the intensity, right. And you know that how to calculate the structure factor. We are not going into detail because that depends on atomic scattering factors. and then you have this relation, right. In the last class we did this example. Anyway, I will go over it one more time so that it is very clear. So, we are now considering a diffraction pattern from this FCC structure copper, a copper which has FCC structure, right, face centered cubic. Suppose you get a diffraction pattern, right. Now, we are trying to calculate the intensity, right, and see whether our calculations match the observation. That is the idea, right. So, I will not go again in detail, but just to illustrate, to calculate intensity you have to calculate the structure factor, that is one of the important factors, and we saw that for different conditions you can get different structure factors, right. Again it depends on your expression. So, in this case you see when you have a mixed indices your structure factor is 0. So, even though there is a plane, depending on HKL, right, you will not see any reflection, you will not see any diffraction from these planes, and for some planes where you have unmixed indices you will see diffraction. All you know this, right. This is based on the conditions. So, now you know the HKL, like the planes where you are getting diffraction, clear from this. So, you know these planes, we have written it here, column 2 HKL, right, 1 1 1 2 0 0, these are the planes you are getting diffraction from based on your structure factor calculations. Please refer to earlier lecture if you are not clear about this. So, now once you know HKL you can calculate this term h square k square l square. See again why we are again looking at h square k square l square, you have to always remember, see we are talking about this relation, one is Bragg's condition, okay, and the another is interplanar spacing for the cubic crystals, right, that is right. So, Bragg's condition and your interplanar spacing. Now, you can eliminate D and you see that there is a relationship between HKL and so the term you are interested in is h square plus k square plus l square, right. Basically further if you do calculation you will find this expression, right, or you can write it as h square plus k square plus l square over sin square theta is equal to 4a square over lambda square, right. Now, if you know the crystal, if we are talking about the cubic crystal, so A is defined, A is constant, and we are using monochromatic X-rays, lambda is fixed. So, this right hand side is a constant. What does it tell you? It tells you your h square k square plus l square is proportional to sin square theta, is not it? Okay. So, we will use this. So, now you see why we are calculating h square plus k square plus l square. Again it is on condition that we are looking at copper which is FCC. If it is something else then you would use some different relationship. Okay. Basically it comes from the interplanar spacing. Everyone is clear why we are doing this? Okay. So, 1 1 1 that means h square plus k square plus l square will be 3. For 2 0 0 it will be 4. So, it is easy to calculate this once you know HKL. Okay. Now, we can calculate the sin square theta, that is given here. Okay. And you already know, right, you have a diffraction pattern. So, you know what are the values, right. So, once you know this you can always calculate the theta, right. Once you know sin theta you can calculate theta. So, these are the values you have, okay, degrees. So far good, okay. So, you know the plane, you know the angles, Bragg angle where you have diffraction. this term we are calculating just I think I explained in the last class, because to calculate the atomic scattering factor, remember again, to calculate the structure factor you need atomic scattering factor, and the scattering factor depends on this term sin theta over lambda. That is the reason why we are calculating this here. Okay. So, from this, once you have this sin theta over lambda term, you can calculate the atomic scattering factor, okay, f small f for copper, because there is a dependence. This scattering factor depends on sin theta over lambda. That is the reason why we are calculating. So, there is a table, you can use a table to get this FCU given sin theta over lambda. Okay. Now, you know everything to calculate the structure factor, capital F we are talking about, capital F square, right. Again, let me just go back so that, see, this is the expression for structure factor. Capital F for given HKL depends on multiplication of atomic scattering factor for that atom times this expression e to the power 2 pi I HUN KVN LWN, where HKL are the plane you are interested in, and UN, VN, WN is the fractional coordinates. You need to know the atomic arrangement, because that is going to influence your intensity. Okay. So, this is very important relationship. Okay. So, now we can calculate the structure factor. Once you know the F, you can calculate F square, right. Simply you have to use the same relationship, okay, or you can use the term here, F square will be 16 small f square, right, because for lot of other planes your f is 0. The planes you have considered here, you have capital F is equal to 4f, 4 small f, 4 times small f. Once you know the atomic scattering factor, you can calculate the capital F, calculate the square, because we are calculating square because that is your intensity is related to square of your structure factor. Now, multiplicity factor, okay. So, this is P talked about in the last slide, and this is your Lorentz polarization factor LP, 1 plus cos square 2 theta over sin square theta cos theta. Rather than going into detail, we can just you can calculate this, right. This combines your Lorentz factor and polarization factor. Okay. Now, you know everything, assuming there is no effect of temperature absorption in this case, what you can do, calculate the intensity, right. F square times P times Lorentz polarization factor will give you the intensity, right. You just have to go to this equation, you know this, you know this, you know this. Let us keep it, we do not consider this for now, okay. So, you get the calculated intensities as these ones, right. Simply you have to do multiplication. Now, we can normalize it, right. It is difficult to see. So, what you can do, you can assume this is as like, you can normalize it, and then you can say, okay, if it is 10, then this will be 4.7, right. You can normalize it, right, this x. So, you get these numbers. So, line 1 has intensity of 10 counts for an example, line 2 4.7, right. This is just simple normalization. What does it tell you now? So, see, if you see the intensities of all these lines, which one is the strongest line? Line 1, right, because then comes line 2, right, I mean at least from this calculations, right. Then you have very low intensity also, 0.9, 0.6 for an example. So, this is the calculated intensity. Now, if you look at the pattern, the observed one, what does it tell you? Vs is very strong, Vs means very strong. Doesn't it match? So, it says that line 1 is the strongest, also matches with your calculated intensity, right. And also you notice this is the weakest, weak, this is weak, M is medium, S is strong. So, very strong, strong, medium, weak. So, see, just this simple calculation can give you the relative intensities. So, now you have basically you know where are you getting diffraction and where what will be the intensity of the peaks. Okay, is it clear? Yeah, so this is the expression we are using in this case. Okay, a few more things. So, how do we decide which are the planes, right? HKL for an example. So, again we will come back to this relation. Again it comes from simply first Bragg's condition which has to meet for diffraction, and also this interplanar spacing. So, in this case cubic system you can say that sin square theta over h square plus k square plus l square is equal to lambda square by 4a square. This holds for cubic system. So, now we can get based on this what are the possible values of HKL, what are the possible values of HKLs. So, you find that for simple cubic, if it is simple cubic, your h square plus k square plus s square will be either 1, 2, 3, 4, 5, 6, 8. Why not 7? Because you can't get any combination to have h square plus k square plus l square equal to 7 simply. So, if your plane is like 1, 0, 0, your h square plus k square plus l square is 1, right. So, see 1, 2, 3, 4, 5, 6, 8, there is region 9, 10, 11, 12, 13, 14, 16. For BCC, right, your BCC body centered cubic, here these are the planes h square plus k square plus l square will be 2, 4, 6, 8, 10, 12, 14, 16, right. FCC, this is the sequence, again tells you for cubic system, right, this is for diamond cubic. Okay. Now, we will try to use it. So, finally, we want to know how do you determine the crystal structure, one of the questions I would like to address. Now, you know, okay, you have a diffraction pattern, what gives rise to different values of 2 theta, what gives rise to difference in intensity. Now, someone gave you a pattern and asked you how do you determine crystal structure, right, that is also important question to answer. So, if you know the diffraction pattern, you know the values of 2 thetas, right. So, these lines you already know from a diffraction pattern, right. So, let us assume that we have 2 theta versus intensity plot, right, that is a typical plot, typical diffraction plot. So, you have 2 thetas, you can always convert to theta, from 2 theta you can calculate theta, right. Then you can calculate sin theta, finally sin square theta. Why we are doing sin square theta again? See, remember this is very important relationship. We are talking about, yeah, so for cubic, right, you have h square plus k square plus l square proportional to sin square theta. So, we already know sin theta, sin square theta. So, we try to, now you have this sin square theta values, right. Now, they are expressed as 0.11, 0.14, does not make sense, right. We have to somehow get values of these HKLs, right. So, what we say, we normalize it again, we try to get rid of these decimal points. So, the ratio basically we have to maintain this ratio, we can say that this will be similar to this, right, it is nothing but normalization. Okay. So, you can express it as in this ratio like 3, 4, 8, 11, 12, 16, 19, 20. Okay. Maybe you can multiply it with some factors, then express it in whole integers, that is the idea. Okay. You can do it, it should not be difficult. Now, once you know these ratios, it tells you first of all immediately, once you know that 3, 4, 8, 11, 12, right, it is like FCC, that is the power. So, you can tell, okay, this is FCC. So, now to get h square plus k square plus l square is equal to 3, you need to have HKL as 111, right. So, now you write the index, 4 possible is 200, right. So, you can write these planes here, right, and you can also calculate the d values, right, for these planes, right. So, finally, let us use this relation Bragg's condition lambda equals to 2d sin theta, that will hold at all planes wherever you have diffraction. You know lambda 1.54 angstrom. Let us consider this line 1 where you have a d11. So, it can be written as 2d11 sin theta 11, right. Now, since it is cubic abscissa, we can write this d in form of lattice parameter. Again, I am not going back, but you can simply review this, you will be able to find the relation between d and a. Okay. So, a over root 3 sin theta 1 we already know, okay, sin theta. So, from this basically idea is you can calculate a. A is the lattice parameter you are looking for, it is abscissa. Once you know, it will be same in all direction, it is a cube. So, once you know the a, you know, okay, this is aluminum in this case, right. So, you know the lattice parameter, you know the what is the crystal system, right. So, this is a simple example, but tells you that you can determine crystal structure, okay. That is what Bragg did, right. Diffraction was known before Bragg, right, but he used the diffraction to determine the crystal structure. Okay. So, let me summarize what we have learned so far. The line positions, or what we mean by peak position, XRD peak positions will give you information about unit cell, shape and size, okay. Or you can say that they will dictate your position, because that unit cell like shape and size of unit cell will dictate where you will see the diffraction, and the intensities will depend on the atom positions. Again, you can refer back to our calculation in the last lecture where we calculated that. So, depending on the atomic position, you may not even see reflection or diffraction, okay. So, two important things, line positions will tell you about unit cell, its shape and size, and line intensities, atomic position, okay. Okay. So, that covers the basics which we need to understand the application of X-ray diffraction, right.